me say, got it. Thank you, Mingling. It was a really nice, introduction, and I'm really happy to be here with you guys. It's a great pleasure to give this talk, especially to a group at Brown University and Professor Konstantinos, who's an old friend, who actually is father of this young research in the confluence of artificial intelligence and numerical modeling, the way we coined here at University of Illinois. So let me say a few words. People have said many times recently, actually, AI is the new electricity, right? So just like in the dawn of 20th century, when my old countryman Nikola Tesla, when he invented actually induction AC motor, kind of changed the world at that time forever. So we witnessed the same thing with AI nowadays, and numerical modeling in science engineering is no exception. With classical methods, which started actually confluencing with AI, and then we use that to accelerate challenging simulations, designs, optimization, even solving previously unsolved problems. We at University of Illinois, especially here at NCSA, we have been highly engaged with this research, and I will show you some of our exciting research developments with direct application in industry as well. I don't know if Diab, Dr. Diab Abueidda is here. Diab, are you here? He may actually join us later. So he's the research scientist who is co-leading this research at NCSA with me. So let's start with this kind of outline of my talk. So we're going to do a little bit introduction to modeling simulation, classical way, especially with HPC mingling. I think I was mentioning petascale, so I'm going to show you what we did there. And then the rise of this fourth paradigm in science engineering, which is actually data-driven thing. We're going to talk about data-driven neural networks that we have done most of our work, but then we will also show you our work with pins, especially in the CFD and CSM, and then hopefully we're going to leave some time for questions and answers. A few words about our center for people who don't know what NCSA, what we do. So we are originally funded by NSF in '86. We host some of the largest cyber infrastructure in the United States. We also providing expertise, a level of support for our users. We work both with industrial and academic societies. Research societies. So we are the home of the first successful web browser, Mosaic, in '93. We also deployed the first Linux Itanium-based cluster in 2001. And then I'm sure most of you are also users of Seid, which is a large NSF-funded project to provide actually access to researchers on this side of the pond to HPC, cyber infrastructure, and expertise. Mingling was mentioning the Blue Water system, which was actually at the time largest open science system in the world of petascale level. And we are actually retiring it these days at the end of this year. So I'm going to start actually with a quote from Professor Hughes, Tom Hughes from University of Texas, who is probably one of the largest living professor or researcher at in this computational mechanics, who has said, I was a grad student, a young grad student back in 2003 when I was attending one of those International Association for Computational Mechanics, when he said that the supercomputers are going to be size of the football field, but will be still too small and too slow for some of these calculations. And when you think about, trying DNS intervalless or DNS from the micro level, even in solids, we are just scratching the surface with petascale machines. And there is some hope we're going to be able actually to solve more of that at exascale, but we need some support from other areas, and that's where that fourth paradigm is coming, what I'm going to talk about. So just to give you an example, I'm working a lot with industry globally, and this is actually a quote from Dr. Yun Ho from Rolls-Royce at UK. This was actually at International Supercomputing in 2014. So he said, I have a dream. In that dream, I want to do everything coupled with the engine simulation and design, including fluid flow, stress, and all of these other multi-physics phenomena which are happening. And there's just a quick back on the envelope calculation. So it will take 1 trillion degrees of freedom and 1 billion core hours per calculations, which even on a exascale level machines that are coming, we're going to be a little bit far away from that still. So these are actually some of the work that we have done on Blue Waters. So this was actually done with an engineering code. So we were sort of technological evangelists. When we started this journey, the common belief was actually that simulation codes, especially engineering simulation codes, they don't scale very efficiently on large supercomputers. So this has been proved wrong on Blue Waters. So the legacy from this is that feasibility of efficiently solving extreme size, real world multi-physics, geophysics problem on the petascale and potentially exascale level is possible, and it's adding tremendous value to the future science engineering, high fidelity simulations, design and research. Just to give you an example of some of those simulations that we have done on Blue Waters. This was actually with Barcelona Supercomputing Center collaboration. They have a really scalable multi-physics code. It's scaled to 100,000 cores. So we were able to solve some interesting problems, coupled EM with solid mechanics in human heart. This was to date the most fidelity model of human heart ever done. Industrial kiln furnace also scaled to 100,000 cores, and I think we were using LES model for turbulence here. Just to give you an idea for these calculations on a laptop that I have here, which is pretty good laptop actually, it will take probably around 18 years, almost 18 years, what we have done in less than 2 hours on Blue Waters. And another example is the Rolls-Royce, that we actually went through with the commercial code LS-DYNA on many cycles of improvement. And finally, we ended up actually having performance 2 orders of magnitude better than when we started between 4 walls at Rolls-Royce. Okay, so so much about these classical deterministic methods done on HPC. As you can see, lots of has been done lately, but we are still lacking the power, computing power, enough computing power. So this is actually what I'm teaching kids here at UOI. I like to show these 4 paradigms. So historically, we were first at the first paradigm where people were actually scientists were observing empirically, and then they quickly realized they need some models, some governing equations actually to solve some of these phenomena of the interest. So we ended up with the governing equations, PDEs, ODEs. We then quickly realized, the closed form solutions coming from math are very few. So we started actually doing numerical analysis on small, medium size, big computers that you can see. But, again, there are some limits there. So around 10 years ago, we started actually doing this Confluence, started actually learning from data analytics, applying artificial intelligence, machine learning, and trying, accelerating the third paradigm, but also starting to being able actually to do solve some unsolvable problem. So second, I already mentioned what Professor Andrew Yang says about AI. The second one is actually coming from the leading scientists at the Google Brain, who said, what is cutting edge in AI will become commodity. And that's really happening in just a few years. So I'm pretty confident, these cutting edge things that we are doing nowadays in the confluence of AI and deterministic methods are going to become actually more and more prevalent in science engineering in a few years only. So this is the landscape. we have a first of all, from the historical point of view, AI went through a few AI winters, right? And you know, along with that, also, you know, this kind of AI work. But it's being brightened lately by the development of HPC, especially GPUs, TPUs, where we actually can very efficiently train some of these big models. And then, you know, all of this beauty of Python and, you know, open source machine and deep learning libraries like sklearn and TensorFlow, PyTorch, JAX, for example, new kid on the block. And, you know, pioneers, particularly I'm mentioning this group from Brown and Professor Konstantinos, who has been kind of father of all of this, but then others too, like Professor Raisi, I think, who is on University of Colorado now, Professor Bessa from Netherlands, and others too, you know, and the rest of us who are actually, who got inspired and, you know, move on with this. On the right-hand side, you can see a landscape of neural networks that can be done to actually solve some of these physics problems. On the left-hand side, you know, if we don't apply any physics, then we are relying on actually data only. And in data only approach, one thing is actually maybe we can generate data from modeling simulation on a big machine and then train the model. We have done this on a few occasions. On the right-hand side is the other extreme. It's actually, we don't have any data, but we know the governing equations, we know the boundary and you know, initial conditions, you name it. And so we actually go and use the pin to do the forward solving, and we can solve the problem. But the place in the middle, the space in the middle is probably the most interesting, where we have some kind of combination between data and we know the governing equation, so we can actually solve some of these problems which are unsolvable otherwise, or, you know, they are not totally defined, they are kind of ill-posed problems. Just to quickly, you know, everybody's talking about standard machine learning versus neural networks. So this is one of those benchmarks we have done 3 or 4 years ago here at NCSA. So we have shown actually that traditional machine learning algorithms, they're good, you know, but the problem is actually the accuracy is limited. So even if you throw much more data, the accuracy is going to be pretty much the red line. But if you use actual neural networks, especially deep neural networks, you know, the accuracy is going to go up. But, you know, like everything in life, there is no free lunch, right? So that price that we pay is actually much more computing. And you can see actually a runtime comparison between random forests and some of the very deep neural networks is significant, but of course, accuracy is much better. Yeah, the good news is actually, as I said, GPUs, TPUs, they can really train neural networks very quickly nowadays. So quickly about, you know, this is probably, you know, everybody knows how all of this works, but just quickly, neural networks, a special kind of machine learning, which is working with various types of artificial neural network, which are, by the way, inspired by the brain structure and functionality. So it comprises of layers of interconnected individuals, which we call neurons, that map the input. So input is moving from left to the right. Depthness of the neural networks is controlled by the number of these hidden layers, which are layers between input and outputs. And as I mentioned, after each forward pass, we are kind of estimating the difference between predictions and targets. And then in a backward propagation, we'll calculate the gradients of that loss function with respect to weights and biases, and then update weights and bias and go in around until we actually see there is no probably improvement in accuracy anymore. FL here, or sigma L here, is a special function which we called you know, activation functions, which is some kind of easily differentiable question, nonlinear function that helps neural network actually to learn complex functional relationship between inputs and outputs. So this is actually our surrogate, purely data-driven model kind of cartoon here, what we are doing at NCSA. The major idea is that in the surrogate data-driven model, we'll train the artificial intelligence model to do some difficult time and computational consuming modeling operation very efficiently, such as modeling of highly nonlinear material structural optimization, uncertainty quantifications, even turbulence in fluid. I'm going to show you some of those examples. So on the cartoon network, you can see we use HPC actually to generate a large amount training and testing data samples. So we use modeling itself actually to do that. Then they're all corresponding different modeling scenarios, boundary condition, parameterizations. Then we right away split training and testing data so that neural network never sees the testing data. Then we move to GPUs, which are usually adjacent to these big CPU systems, and to train data, validate with testing. Then the magic happens. The trainable parameters, weights and biases can be transferred to any low-end computing power platform like a laptop or even iPhone. And then the optimal and accurate solutions can be found instantly for any variations of input parameters without HPC or modeling software. So overall, this is not science fiction. Actually, I'm going to show you two examples here. So the first one is from the topology optimization, which is a numerical method that optimizes material layout within a given design space for a given sets of loads, boundary conditions, and constraints. And the goal is actually to create some kind of structure which is strong, lightweight, and minimize material usage. Think about our body, for example. It's very topologically optimized structure with bone material put only where it's needed. Otherwise, we'll be really heavy, not be able to move, right? So we use actually 13,000 topological optimization scenarios that we created on HPC with random optimized parameters to train a surrogate CNN-based model with 3 different objectives. And once the model is properly trained, we can see that we can get optimized shape instantly. And then we can, from that, for this particular paper, we actually use to reproduce, actually to build a new material with that cell with special property that doesn't exist in nature. You can see the predictions on the right-hand side. The second one is actually even more interesting. So the second one is this case of solidification of the steel, where highly coupled nonlinear multi-physics viscoplastic phenomena is happening. So we use actually inputs which were the displacements on this area where the let me see if I can find the. Looks like I lost my mouse. Oh, it's here. So in the area where the mold is touching this new solidifying steel, we actually, the two important things are to apply proper taper, but also, to actually extract all of this heat with some kind of flux. And, those sequences of these displacements and fluxes are our input functions. And then as an output, we are actually predicting the viscoplastic stresses which are happening inside the solidifying steel, but also the temperature within that model. So it turned out actually that sequence deep learning methods were able to, for the first time we demonstrated that how these innovative sequence deep learning methods, such as temporal convolutional network, can learn from the sequential modeling data and reproduce the complex history as well as time and dependent phenomena for these complex materials. The next one is, again, purely driven model that we did, but actually here we use the inverse. So this particular industrial process is actually frontal polymerization, which is a relatively new and fast process in manufacturing of fiber reinforced polymer matrix composites, which are critical in aerospace, marine, automotive, energy industries. With this frontal polymerization, a small thermal energy input is enough to make the entire container of liquid monomer, and with all of these fibers. So the forward analysis here is a typical numerical analysis, which is actually based on chemical composition, fiber volume fraction, and chemistry. We are through these ODEs, which are governing this process. We actually getting frontal characteristics like a speed, maximum temperature, Q degrees, and all of that. The more interesting problem is actually from the manufacturing point of view is inverse problem. So if I have some kind of desired fabrication strategy, what would be the chemistry actually to achieve that? And you can see, there is no way in the world that from the math we can actually get that relationship. Well, we can get it actually from neural networks. So what is the output for this forward analysis, classical forward analysis becomes input for the neural network and vice versa. So we were able actually to get this and also published in a good journal recently.
Sorry, I have a quick question.
Sure.
If you go back to the previous slide, I see that the magnitude of the inferred of your unknown parameters is really big. So did you do any normalization in your data, or you just use the?
Yes, normalization definitely was done. There is a huge discrepancy between these values, so we were actually made sure that we normalized them, put them all on the same level. Yeah, that's a very good question.
Yeah, and also you use pins to solve this, or? No,
this is actually pure data.
So pure data driven. Okay, I see.
Yeah. So pin is next. So I'm going to talk about pins now. And again, without pretending to actually to preach to the preacher, just quickly, physics-informed neural networks, they are usually used to compensate for limited data, right? So the algorithm itself is enriched with the physical laws governing the problem ahead. And the residual of PDs, you can see on the yellow, on many collocations point in the domain or in the boundary conditions is actually part of the loss function. And obviously, pins can solve forward solve the PDEs, but they also can discover PDs, or they can actually solve incomplete problems, models with incomplete data. So let's go to simple problem first. 1D problem, which is actually simple harmonic 1D oscillator with underdamping friction force, which is basically a homogeneous second order ODEs, and we can get the solution, which is oscillates around the equilibrium point with amplitude decreasing with the time, and which is a great thing actually. So we can use and test some of these different scenarios. Again, our physics pin is actually, we have input coordinates, which are times, and then we are getting this displacement as an estimate, but we can, with automatic differentiation, we can easily get the derivatives, so we can actually fit the PD. These are three scenarios, really nicely explained here. So what is happening, the first case is actually O-driven, all data-driven, just like the previous cases that I showed you, no physics there. But the catch here was actually we put only the points on the left-hand side, only on earlier times, and we tried to fit neural network, and you can see it did pretty good job where it knows this information, but for the rest, it didn't know. The second case is, remember my graph, so we are now going actually 100% physics and force. So our loss is not only the ODE, but it's also the boundary condition that we impose, which are both essential boundary condition and the natural boundary conditions. And you can see, again, you can barely see any difference between the analytical solutions and the PIN solution. But what is most interesting, actually, the third case. So in third case is actually we are doing the combination. We use the same data points that we had before, but we are also imposing the ODE. But one thing is actually we didn't put was boundary condition. And once we run that kind of pin, actually you can see that the pin itself was able to discover boundary conditions, and incomplete problem was solved with this combination. So let's go on a little bit to now to turbulence. So turbulence, as you guys know, is the oldest unsolved problem in physics, and still impossible to describe and predict a large Reynolds number. Your friend or your enemy, actually, if you compute, for example, from DNS point of view, is that computing is actually proportional to the cubic of the Reynolds number. So if you increase your Reynolds number by 2, your computing with DNS is going to go almost 10 times, 8 times, right? So, and so on. But people invented some ways around. So we have, RANS and K epsilon models, but accuracy is not good right there. And so what is actually interesting with the K epsilon, they have 5 adjustable constants, and they in their transport PDs, which have been determined by numerous iterations of data fitting for a wide range of turbulent flows, but they were never actually find an optimal solution for a particular flow. So we thought this would be a good problem for for a pin, sort of pin. So we are using actually a neural network that uses coordinates and velocity as input to predict kinetic energy and dissipation of the kinetic energy, or K and epsilon. The turbulent kinetic energy and its dissipation, we pick some flow that has those things, from better models like LES or DNS. So we have some targets there. The loss function, as you can see, is a difference between obviously estimated targets from DNS, but also, we are putting these 2 transport PDs for K and epsilon, which include those 5 parameters that I mentioned. In TensorFlow, actually, we can make those 5 parameters also, parameters sort of, so that they get improved as well. So not only the weights and biases from the neural networks will be updated in each epoch, but also these 5 parameters will be updated as a TF variable data type and with automatic differentiation, right? So at the end of all of this is actually, we ended up with the optimized parameters for a specific flow. Just to give you a quickly example, was actually flow over the bump, turbulent flow over the bump. So you can see the first DNS solver. You can see on the red the estimates of the K epsilon parameters. You can see the default K epsilon solver, and you can see kinetic energy more like resembling the DNS with K epsilon once we actually engage these parameters. So the DNS simulations, to give you an idea, it takes weeks and months on HPC, while K epsilon simulations you can do in minutes and hours. In terms of velocities, we can get about 22% error reduction with respect to these tuned K epsilon model compared to just the standard one. which is actually pretty good considering that industry is using these K-epsilon models all the time. And if you can improve some of these calculations by quarter by 25%, I think you are in a good shape. So just to quickly summarize this, this work in tuning K-epsilon turbulence model, PIN is used as alternative model for tuning K and epsilon parameters. Loss functions was accounting for both data loss between DNS and neural network and physical loss, from the two transport PDEs. In addition to, as already said, that in addition to weights and biases from the neural network, we were actually in each epoch we were, updating those K-epsilon parameters, 5 of them. For the flow over the dump, the velocity error is reduced by 22%, and you can't expect miracles. RANS is inheritedly simplified, but to expect more improvement, but it is still significant, as I mentioned, RANS K and epsilon, which are order of magnitude more computationally efficient than DNS. So the second one is our newest paper, where we believe we were the first of, if not the first, one of the first, if not maybe the first research group that actually used the pins in a nonlinear 3D solid mechanics. The 3D equilibrium PDEs, it pins loss, and it's enforced in the collocation points. Of course, we have many of them, but just showing you as in a cartoon, they are the red ones. And then we also have, both the, essential boundary conditions displacements with the yellow ones, and then natural boundary conditions, which are surface reactions on the blue ones. No data is generated, so this is again one of those examples that we are using. It's to forward solve this problem of solid mechanics. So we actually use 3 cases. So we use the linear elasticity, we use finite strain hyperelasticity, which is a example of geometric nonlinearities, and we also use the plasticity, which counts for material nonlinearities. The sampling of these collocation points is done by Monte Carlo. We didn't use finite solutions at all. So again, there is no data used from finite element. It is just finite element is used for the pins validation. So we use with trial error, we come up with the 6 hidden layer neural network with we are varying the number of neurons between 40 and 60. I think it went all the way to 80. Quite a bit of collocation points within this domain, all the way to 15,000. And then we found out actually that it's very important to put also enough of these points on boundaries. So we use between 4 and 1,000 points on the boundaries. 10H is activation for hidden layers, which is a twice differentiable. If you think about governing equation, is a twice differentiable too. So you better have a good activation function they can do that. We use the we were advised by previous works in 2D that combination of Adam plus LB FGS, which is a second order optimizer, was the optimum one. Again, this was a very new work that we have done. We kind of pioneered into this 3D solids. Let me show you some results. So the first case was linear elasticity. Equilibrium equation is actually, that's divergence of the stress field. We have the essential and other natural boundary condition. In this case, actually, we use only essential boundary conditions. The strain definition in small strain definition, linear small strain definition is actually just a gradients of displacement. And then linear elastic Hooke's law was used, to establish the stress strain, the constitutive model actually combination. And you can see on the right-hand side, we start with sampling the points. We initialize weights and biases, and then we go in a big epoch loop, right? So we obtain the displacements from the deep neural network. We easy to compute their derivatives, which are basically strains in this linear problem. Then from the constitutive point, we can compute the stresses, and then we go in a loop. And if we are within the inside domain, we compute the derivative of the stress, which is actually our governing equations. If we are on surface traction boundary conditions, then we compute the surface traction, and then we can calculate its contribution to the loss function. And then if we are on the essential boundary conditions, we can just calculate based whatever is value for boundary condition. We can calculate that contribution. And so just to give you some examples, so go back, actually, you can see this AB line. So we do that AB line to kind of compare results on the displacements. You can see that pin was matching FEM. Again, FEM was used only for the validation very well. You can see on the 3D contours too. We were able actually to estimate 1 meso stresses as well. What is important for this one, we found that LBFGS optimizer can solve alone too without any combination, but it has a faster convergence rate but slower execution because it's a second order optimizer, right? Adam plus LBGF was faster, but you can see here, actually, this is where we stopped with Adam. It's a different gradient here. So Adam was very sensitive, actually, to the number of collocation points. And then with respect to number of nodes on a hidden layer, less error with 60 or more nodes per hidden layers we have noticed here, which are no surprise. So let's move on to second case, how we do with time, 43, okay. So this is actually a second case, is a case, as I said, where we have geometrical nonlinearity. So this is actually hyperelastic constitutive lobe used to model rubber-like materials that respond elastically when they are subject to very large strains, very large deformations. They account for both nonlinear stress-strain relationship, while also the large shape. So that's why for example, the stress has to be actually defined with respect to initial configuration, which was not the case from the previous case, where we're in a small linear regime, they're kind of same. Here, actually, we have special measurements for definition for stress, which is called first PK, Piola curve of stress, and the Cauchy-Green strains. And then the constitutive model itself is a little bit more involved. So we have a strain energy density, and from there, actually, from derivative of that, we can get the first Piola curve of stress. And then from there, actually, we can get even the Cauchy stress, which is kind of more interesting stress, which is defined with respect to the deformed configuration. So similar to linear case, we sample the points, then we go into the neural network, we get displacement. So we actually compute displacements with respect to initial configuration. Then we compute the deformation gradients, and then from deformation gradients in this constitutive model, which is based on strain energy density, we can come up with the first Piola curve of stress, and then we can actually calculate Cauchy stress if we have to. Similarly, if we are in interior from the gradient of the first Piola curve of stress, we can enforce the governing equations, which is also defined with respect to initial conditions. And then if we are on surface reactions, we can get loss from that part, and similarly, from the essential boundary conditions, we can get the loss from there too. So how all of this works with the with respect to results. So you can see the now along those AB line, we have a nonlinear relationship between displacements and x coordinate, and again, we were getting good, correspondence between that displacement and the finite element solutions, and you can see also on the 3D contours. So what is important here is, although the problem is still path independent, so that means that the stress only depends on the, it's non-linear, but only depends on the current strain. If you use the classical finite element, it will go through the Newton-Raphson iterations, and to avoid the divergence. Why? With just one, through the whole loading history, the one training cycle, let's say, we were able to get these results in a single load. Unfortunately, this is not the case with the third case. The more complex case is actually material nonlinearities with the plasticity. So in plasticity, it's a path-dependent phenomena. Stress depends on the strain history, and that's why we have this yield surface in stress space, which is kind of showing us mathematically where there is an onset of plastic deformation, and that plastic surface in the stress space is changing in size, which is this contribution here, which we call isotropic hardening, and it also can translate in a stress space with this back stress Q here, which we actually called mixed hardening. So in this case, we actually use the combined mixed, isotropic and kinematic hardening. Flow rule determines the amount of plastic deformation, plastic strain, and then we have a bunch of other things. So what is usually used to solve the these highly nonlinear problems, plasticity, is a radial return algorithm that given the state from the previous load, you can get estimate either from finite element or from the neural network of the new displacement. Then you can calculate the strains, but then you try actually and see if you are within the yield surface or not. If you are not, then you have to calculate, some of these flow factors and update actually back stresses, plastic, strains, plastic, and contribution to the overall stress and all of that. So on the right-hand side, you can see we start here with again the estimate of the displacements. Then we use the automatic differentiation to get the gradients of the strain. This is a case of plasticity with small strains, so we can easily get to the small strains. Then we check if we hit the trial. We try the trial, condition and see if we are in plasticity area or not. If we are not, then we are elasticity and everything is easy. We just update it. If we are not, then we have to update the flow strain, flow stress, and then update the plastic strain components and stresses. Again, similarly, if we are in the interior of the domain, we use the divergence of the stress field actually to enforce the governing equations. If we are on the surface boundary, then we calculate the surface attractions. If we are on the essential boundary conditions, we actually calculate that contribution from the to the loss function. So again, since this is a path dependent phenomena, we had to divide the loading history in kind of quasi-static time, increments, and you can see 4 of these increments. Every time you have to, just like finite element doing with Newton-Raphson, we have to actually train. And you can see for a small, displacement, there's quite a bit of, problems in the beginning with convergence. But then as we are going to later loads, especially the last one, you can see the loss function right away starts with a smaller value, and then the convergence is easier. So why is this happening? Because we are actually using the transfer learning. So the outputs of the weights and biases of the first load increments are actually inputs for the second one, and so on. So convergence at the later load, as you can see, is up to 3-4 times faster than initial load increment. And this is actually very interesting. So for all of you guys who are, calculating, who are doing nonlinear finite element, especially with large loads, that the convergence become worse and worse with abacus or ANSYS as you are actually approaching the end of the loading history. While here is actually the opposite. So give us some hope that these pins in nonlinear solid mechanics may be actually on a larger scale, 3D scale, maybe actually more computationally efficient than traditional finite element methods. Again, some results, they look good. We were able even to estimate plastic strains and, in a couple of directions, one mesostresses and all of that. So let's go to conclusions. Physics-informed neural network was able to directly solve the governing equations which are governing the stress generation in linear, nonlinear, 3D solids. No data generations is needed, such as surrogate deep learning models. So the spin was actually able to do everything on its own. Since spins or every neural network relies on simple linear algebra, which are very well optimized on GPUs, why standard finite element and nonlinear finite element, they usually use sparse direct solvers in implicit finite element method. That will be interesting comparison. Who is actually faster, who can faster get to the results. We also noticed remember those penalty coefficients, which are kind of weighting the contributions of the boundary conditions in a loss. They are very important, so we come up with them with trial and error. When it comes to discretization, with just collocation methods of complex geometries, it's probably easier. When you remember a classical finite element, you have to make sure that the aspect ratio of elements are not exceeding certain threshold. And, there's a sampling in the global stiffness metric. And then I said, most of these commercial packages are using direct numerical solution, which are the only robust one, actually. If you look at the CG methods, they sometimes diverge. I already mentioned this transfer learning between the load increment and plasticity made actually convergence of pins faster at later increments, and opposite is often true in nonlinear finite element, unfortunately. LBGFS being high order and more accurate optimizer is slower than Adam, but we actually tried to play it with just LBGFS for plasticity, and we were not able to get the good convergence. So our assumption is actually it probably being very precise, it was able it was actually got stuck in a local minimum in plasticity. Why Adam, being more forgiving, actually was able to avoid those local minimums, and then once we switched to LBGFS, it was able to go to the global minimum easier. So what do we do nowadays? Or considering to do, again, test 3D domains with irregular geometries and high solution gradients. So this was all very structured problem with just rectangular beam being under bending. I already mentioned this test the computational performance on pins on latest GPUs versus classical FEM, especially on the large domains with lots of these collocation points. Test resampling of the points between training iterations and assess the impact of accuracy. And this itself could be an issue for path-dependent behavior, such as plasticity and viscoplasticity, because if you introduce the different sampling points, then you are violating that path dependence of them, because they are different points. Test how well the transfer learning works with different loads and boundary condition. This one is important, actually. There is the paper from Fogg and Boclas that I was actually one of the reviewers there. They did a really interesting problem, which reminds me actually to deep nets. So they actually estimated, in addition to displacement, their neural network was also, calculating stresses. So basically, you get stresses from neural network, but you also can get stresses the way we did from the constitutive model. So you can compare those two stresses, and their difference can be also a part of overall loss function. And it is believed, at least in 2D, that it was able to improve some of these stress results, especially in these areas of large gradients, holes or some kind of irregular geometries. We are also working on the deep energy methods, particularly for viscoelasticity, where instead of strong form of governing equations, actually we are using the weak form, some kind of functional there. Best of our knowledge, nobody compared pins and DEMS yet. I'll be an interesting comparison as well. And then deep nets, right? Everybody's talking about deep nets nowadays, where wherever I go, actually, I show this, what we have done with pins, especially in 3D solid mechanics. But they can just solve every time one instance of sets of boundary conditions of load or something else. But what people are more interested in is actually solve them in a parametric fashion, sort of, when boundary conditions itself are becoming parameters. And one way to do it is actually with these deep nets, where you are learning the operators instead of just solution functions. And if you they are incredibly computational intensive, because you are adding these parametric functions into this mix of trainings. But if you are successful, you have a good HPC, for example, you can do that. Then you can actually get solution of some of these engineering PDs with some of the parameters, which I believe is going to be focus area for all of us in the future as well. To finish, training data always important. So this is actually attempt of everybody's talking that at some point AI is going to try to overtake the world. So they look at the data of humans and they figure out actually most of the wars were with the spears and arrows. So they attacked humans with that instead of nuclear bombs, for example. So they were quickly defeated by humans. So be always careful with your training data. And thank you again. I'm sorry, I almost hit the top of the hour. So
thank you, Dr. Koric, for your wonderful talk. Is there any questions from the audience?
Hi, Dr. Koric. Yeah, my name is Enrui, and I'm a PhD student in George School. I have a question regarding the case that you showed about the cantilever beam for linear elasticity. Yeah, so I find that in the result that you get, yeah, it matches quite well. Yeah, actually, previously I have also tried this problem, and according to what I observed, is that because for this case there will be some like stress concentration at the left boundary. Yeah, because you essentially clamp. Yeah, I essentially clamp that side, and there will be some stress concentration at the top and the bottom edges. Yeah, of the left cross section. So I was wondering whether you have observed the similar thing, and does the pin also give you the similar results, like able to reconstruct the local stress, the stress concentration or singularity of the stress?
Yeah, that's a very good question, Andrew. Even with this very structured geometry, like you said, you know, close to boundary conditions, for example, that there are higher gradients, right? And you know, the way we solved that problem was more like a brute force, right? So actually, we put lots of collocation points there, you know, where the gradients are kind of expected to be high. But remember what I mentioned. You know, this mixed approach where we're going to be actually estimating stresses in addition to the displacement may actually help us to alleviate some of these problems in the future as well. You know, yet to be seen how all of this is going to work in 3D.
Okay. Yeah, thank you.
Any more questions?
Hi, Dr. Koric. This is Leo from Crunch, and I have a question regarding your research on the turbulent modeling. Basically, you are tuning the turbulent viscosities using pings. And so my question is that regarding the generalization, so you use the DNS data to tune the K-slope model, and is that the coefficient that you get from one case can be translated to other different cases? And have you done such exploration to generalize to other cases?
It's another great question, Leo. I think we can come up some kind of catalog of similar flows, and you know, instead of going to each particular flow, I think we can find a family of similar flows, and then for that family of similar flow, hopefully, you know, there will be one where you know, there is a DNS data or LES data for K and epsilon. So we're going to be able actually to create, you know, optimize the parameters for that, and then, you know, use that actually to improve the K epsilon. You know, so that's the idea. And then the industry itself is very interested in this kind of approach, you know. So for them, you know, they have a flow in certain mechanical part, and you know, they change some of these external dimensions a little bit slightly, but they don't generate a different flow. So if we can come up with some kind of set of these optimized K epsilon parameters, you know, they are very happy if they are getting precision better than 20% like we did, you know, for this flow over the bump.
Right. Yeah. Thanks.
Sure.
I was wondering if some data have any questions, because I think maybe one way to maybe solve the singularity problem that you just mentioned would be minimizing the total energy of the system. Because so some maybe you want to talk more about this.
So actually the comparison of pins and DEM that you were talking about, I actually did it for my fracture problem. I work on fractures for brittle fractures. So I did a comparison, and that's something where I saw that energy minimization does a better job for normally when you're using constitutive laws. If you are using the variational principle, energy minimization does a better job. We did try to solve a couple of elasticity, hyperelasticity problems, and we actually showed that DM is doing a better job than pins in those kind of situations. So
I believe that. I think, you know, Samata, that's why, you know, as I said, next thing is actually we found, you know, the weak form, the functional potential of one of those viscoelastic materials. So that's what we are working on right now, you know, and we will definitely try PIN as well with that. And I'm pretty sure we're going to see what you have seen too.
yeah, like, yeah, we did that already. Yeah. Thank you. Thank you.
Yeah. Thank you too. Yeah. So the question for you guys quickly from the Brown University, you know, those depot nets that you guys have started, you know, how is that all working? You know, is it really, you know, if I have a set of boundary conditions that are going to be parametric functions, our depot nets are going to be able actually to find you know, that the solution in terms of this parametric function? Or maybe is somebody of you working on that still, or?
Oh, actually, I'm working on that now. So we're going to publish a paper very soon on coupling a traditional numerical solver like finite element with a depot net in multi-scale modeling problems. So in that paper, we train a depot net to solve like a linear elasticity problem, elastoplastic problem, and also a hyperelastic problem. And so we feed those data and we generate a lot of data and train a depot net. And then so that the depot net can predict the system response according to a new boundary condition. And then in this way, we couple with a finite element solver to solve the problem. But that's for 2D problem. So in the future, maybe we can consider that consider the extension to in 3Ds. But definitely that's something very interesting. And
Yeah,
I'm glad that you bring this up.
Mainly, we can even collaborate. You know, we have big machines, and you know, we are handling jacks. If you're done with jacks, I don't know what you did. You know, for depot nets. You know, so we can collaborate definitely. You know, try 3D problem as well.
Sure. Thank you. We will. How about I send you the paper when we finish the draft?
Yeah,
if you're interested.
Yeah. Maybe I can give you some suggestions. You know.
Yeah. Thank you.
Yeah. Sure. I don't know. You guys have another talk or?
Oh yes. So is there any?
You don't want to steal too much time from the next speaker. You know. So.
If there's no more questions, so please.
No, actually, can I steal 1 minute from my talk to ask Seid something?
Yeah, please go.
Hi, Seid. Actually, thank you for your talk. It was very motivating and interesting. Just a question about your computational times about the 3-3 problem. Do you have any? Do you remember maybe how much time did it take for deep learning and how much time it took for FEMS?
Is Diab with us? Maybe.
What's that?
It's my research scientist who was actually running. So I was asking. Right. He was supposed to join me, but he said he has some emergency, so probably he didn't. I would say, Kostas, it's we are not talking about days. We are talking more like minutes or hours. You know,
all right.
Especially on GPUs.
Are they comparable?
So that's my next on my list. You know. You know that direct sparse solvers, which are part of Abacus or NCS or you name it, LS-DYNA, implicit LS-DYNA, they are they don't scale very well on GPUs. But you know, sure. all of these things are really good on GPUs. You know, in terms of PyTorch or TensorFlow or JAX. So the comparison will be really interesting. So,
sure.
Especially
sure.
Again, classical finite element has problems at the end of the very nonlinear cycle, loading cycle.
And the problem goes high.
By transfer learning, we were able actually to see quick convergence.
Yeah. All right. That would be interesting. Yeah. All right. Thank
Yeah.
you. Thank you very much. Thanks.
Yeah. Yeah. So Minglang and some data and everybody else from Brown, please say hello to Professor Kardianakis, you know, and we're gonna catch up later. Yeah.
Sure. Thank you.
I'm sorry, Kostas, I have to go.
No, it's
somewhere,
okay.
but
It's okay.
I'm gonna see the recording.
I enjoy that.
Yeah.
Maybe I'll contact you. Thanks. Thank you.
Thank you.
Yep.
Thanks, everybody. Bye.
Yep. Thank you. Bye-bye. Okay, we really need to move on. So our second speaker is Dr. Kostas Siettos. If I
Yeah, sure.
right. Yeah. Sorry. So Dr. Constantinos Siettos is an associate professor at the Department of Mathematics and Applications and the School of Advanced Studies of the University of Naples, Italy. His research is at the trijunction between mathematical modeling, numerical analysis, and machine learning for complex and multi-scale systems to deal with emerging challenging problems in applied mathematics, computer science, physical, and life sciences. He has been awarded the Fulbright Award for Academic Excellence to conduct research and lecturing on complex systems dynamics at Princeton University. He has organized many international conferences. Since 2019, he's chair elected of the advisory board of Dynamics Days Europe. He's also the editor-in-chief of the Elements of Dynamical Systems. So today, he's going to give us a talk entitled Numerical Solution of PDEs and Initial Value Problems of Stiff ODEs with physics-informed random projection neural networks. So please join me in welcoming Dr. Siettos.
Thank you. Thank you very much. First, can you see my screen?
Yep.
All right. Okay, great. Okay, first, I would like to thank you. It's really an honor for inviting me to give a talk at the Center of Physics-Informed Machine Learning. Really an honor. It was actually inspiring the work of the group of Professor Kardianakis to what I will show to you. And actually, what I'm going to show you is how to solve partial differential equations and stiff problems of ordinary differential equations with physics-informed random projection neural networks. And actually, a better title could be, or an equal title could be, the title of Bill Gear, which is a totem in numerical analysis, on a paper that was actually appeared in Science Review in 1981. And the title was A Numerical Solution of, I would say, Differential Equations. Is there anything left to do? And with is there anything left to do is, can we actually beat traditional numerical analysis methods? Okay, and this is actually the bet of using such schemes today. So the outline would be, I will give an overview of what are stiff systems very quickly. And I will refer to the equivalence with the numerical solution of PDEs. And then I will talk about what has been done until now with solving PDEs or ODEs, general differential equations, and how this is connected with the so-called curves of dimensionality. And then I will introduce the method. Actually, I will try to tell you what are the random projection neural networks and how they can be connected to physics-informed neural networks. A close concept that is extreme learning machines, and I will tell you also how one can construct also bifurcation diagrams of nonlinear PDEs. And I will conclude by showing to you some strong evidence of the performance of the proposed method in both benchmark problems of ordinary differential equations and partial differential equations. Some benchmark problems are the sampling gear problem, the Van der Pol and the Hires, while from PDEs I will show you the 1D nonlinear viscous Bergers and 1 and 2D Uvilbrat-Gelfand problem. And then I'm going to show you also some interesting comparison with, especially with finite difference and FEMs, but also with standard, well-established used stiff solvers. And both, I will show you that maybe we can do something, we can say something, and we can do something better than the traditional numerical analysis. And this is kind of interesting and gives also motivation to go working on these problems. All right, so actually, let me start with a very brief introduction about the numerical solution of ODEs. And here the central key idea is the Picard's theorem that gives actually the conditions for the existence of a solution to give an initial value problem. Okay, so if you have an initial value problem with, let's say, m first order differential equations, where f is continuous multivariate functions from r times rm to rm in some closed domain D of the space containing the point, an initial point x0, epsilon 0, then if f satisfies the Lipschitz inequality in the domain, then Picard's theorem says that there exists a unique continuously differentiable function which satisfies the system of ordinary differential equations. And actually, this is the heart of numerical integrators, that this function can be actually approximated recursively by a sequence of functions yn, where yn can be actually are defined recursively using this formula with the integral. Okay, and then the uniqueness of the solution is guaranteed by, at least theoretically, by the Lipschitz condition. Okay, and there is a bunch of methods starting from the simplistic explicit Euler, the implicit Euler, and the Runge-Kutta methods, and also they are more advanced, like the multi-step methods of Adams-Bashworth or the Adams-Moulton, which is implicit. And here's the idea to approximate the integral that actually the sequence of y's that approximate the solution by approximating what is inside the integral with a polynomial interpolation, and then integrate the interpolating polynomial. So very briefly, of course, for example, the Adams-Bashworth integration uses, let's say, two points on of the past, if you want, to find the future at solution at time xn. Okay. The thing is that even if f in the operator of the differential operator is smooth enough, the behavior can be complex and actually difficult to time integrate because of the appearances of stiffness. Okay, and what Champaign and Gear defined as stiffness, a stiff problem, is that they are the ones which integration with a code that aims at non-stiff problems like the Runge-Kutta or explicit Euler, let's say, proves conspicuously inefficient for no obvious reason, such as, for example, if we have a lack of smoothness, but this is not the case, right? Or the presence of singularities. And what I would like to say, and this is something that also was highlighted in the paper of Champaign and Gear, that stiffness should not be confused with the appearance of steep gradients in the solution. So they are different things. And actually, a problem that proves that, very simple, is the van der Pol relaxation oscillations, where exactly where the steep gradients occur, where the solution is almost singular, the equations are not stiff. All right. So there are two different things, but also steep gradients perplex the time integration, and as I will show you next. And of course, there are methods. And Gear was here. I am with Professor Yannis Kevrekidis and Bill Gear and Prison many years ago. There are methods for actually integrating stiff problems, and of course, it is an open research topic yet after so many years. So let me start saying about the numerical solution of differential equations in general. So let me take this general form of partial differential equation with, let's say, M boundary conditions. L is the partial differential operator acting on U, and F is a nonlinear function of U, and lambda here is a vector of model parameters where we can use to construct, let's say, bifurcation diagrams, etc. And theta U omega lambda denotes a partition of the boundary in M pieces here, okay? And we all know that we can apply terrific methods for discretizing in time and in space, for example, finite elements or spectral methods, or even the simplistic finite difference methods or finite volume methods. And then at the end of the day, we get a system of algebraic equations, and even if they are large enough, we can use the tools of matrix free in the Krylov subspace, for example, Newton GMRS, to solve the system and get the solution, okay? For example, finite elements, we seek a solution in n points by expanding the solution in basis functions that they are defined, so they are also satisfy the completeness requirement. And then, for example, this resembles physics-informed neural networks. The formulation is actually the same. We aim at minimizing the weighted residuals, okay, based on some basis functions. And actually going back now at the decade of 90s, there were the first attempts of using artificial neural networks, then feed-forward neural networks, to solve L-NER differential equations. So one of the first papers was that of the group of Yannis Kevrekidis at Princeton, where he actually constructed a feed-forward neural network to resemble the Runge-Kutta integrator in order to learn and solve a system of nonlinear ODEs. And then Lagaris and Fotiadis at the late 90s introduced feed-forward neural networks to solve simple problems of differential equations. And then again, in the group of Kevrekidis, there was this paper that used Runge-Kutta to solve PDs. And here is a figure of this paper of 1992, where you see that a neural network, a multi-layer neural network, was constructed ad hoc to resemble the Runge-Kutta method. Actually, if you and this is a figure from the paper of 1998, where actually it's the kind of humor me, the ancestor of convolutional networks, as they have used actually a stencil neural network of using finite differences, like convolves the solution in space. So actually, if you think, I mean, we can represent whatever numerical, traditional numerical analysis method with neural networks, all right? So that was the first attempt, and then more recently, there is a big bump in using better schemes due to both theoretical and technological advances. For example, deep learning, Gaussian processes, and of course, the group of Professor Karniadakis has revolutionized the way that we think and solve about both the direct and inverse problems of PDs with the introduction of the physics-informed neural networks and automatic differentiation in deep learning methods. Okay, so let me first make a summary, a very brief summary of what is, let's say, allow me to say, the classical way to solve differential equations. So if we have a time-dependent, let's say, differential equation in this general form, where U satisfies the boundary conditions, that could be of any kind, Dirichlet, Neumann, or Robin. So actually, machine learning solving such differential equations involves the solution of a minimization problem, which is of this form. So actually, psi here is a trial function which approximates, let's say, the solution of the differential equation at space points, but also in time, and is a function of a machine learning algorithm like Gaussian processes or deep learning scheme. P here in the machine learning contains the parameters of the machine learning scheme. For example, in feed-forward neural networks, these are the internal weights, also the biases and the weights between the last hidden and the output layer W naught. Okay, and Q also contains the hyperparameter. So all the problem is finding, optimizing, minimizing this cost function, which contains two terms, the equation per se, and the boundary conditions that have to be satisfied. So we have to find P and Q that minimize this objective function in space and in time, in collocation points in space and time. Okay. What is the problem? The main problem here is that training, especially if one uses deep learning, but also for simple structures with one single hidden layer, is computational demanding. And from numerical point of view, because also of the structure of the problem for which a solution is sought, the problem may become both very large scale and non-convex. Okay, so this numerical at least will not guarantee any convergence. All right, so actually we kind of use many different initial conditions and hope that this will converge. Of course, if converges and we are lucky, then we can approximate with any accuracy if the number of the neurons in the hidden layer are large enough. At least this is what the universal approximation theory guarantees theoretically for even for simple ANNs. All right. The thing is that the problem comes from the curse of dimensionality, and this is a nice cartoon created by Saul Steinberg in 1968, and this is not about the computational curse of dimensionality, but a more serious one, the curse of dimensionality in life. And every day, every minute, we come to take many decisions, and there is no guarantee that our decision is global optimum from all the decisions that we could take. But at the end of the day, we should take a decision, so we should solve the problem. And then here is the curse of dimensionality in training of neural networks and machine learning algorithms. And of course, this comes from the number of neurons in hidden layers, the input dimension, the non-convexity, and also the request of optimizing also other hyperparameters in the network. Okay. So the Gordian knot to the curse of dimensionality came as an idea again from the 90s. Okay, so there was this paper from Smith et al. Where he was actually doing some computational experiments by not trying to train all the parameters of a single layer neural network, like the hidden weights, but fixing them and see what, and he tried to see what he gets in terms of accuracy for classification problems and comparing with the classical way where one could optimize everything. And out of surprise, he realized that if the weights of the internal layer were fixed and they were constant to random values, then he would get the almost or the same accuracy that would get if he would optimize also in the classical way. And this is just some computation experiments. And then Pao, in the same year, came with the concept of random vector functional linked networks, where he did the same thing, but he also used an extra connection between the input layer and the output layer, while now the internal weights were chosen randomly in the interval -1 and 1. And actually, he got the same results. And then in 1995, Interlink proved that the random vector function link networks are universal approximations for continuous functions on bounded finite dimensional sets. And actually today, this kind of networks where you fix the internal weights in fixed values, in fixed random values, come with different names as echo-state neural networks and reservoir computing or extreme learning machines. And again, the keystone idea is to use a fixed weight configuration between the input and the hidden layer, fix the biases for the nodes of the hidden layer, and use a linear output layer. With this way, the output actually is projected linearly onto the functional subspace spanned by the nonlinear basis functions of the hidden layer. And now you came up only with unknowns that they're actually the weights of the out layer, and then you can use a Newton-Raphson let's say, algorithm to wrap around this this map in order to approximate a function. And this is actually what was done by Huang and in a paper of neurocomputing, where he called these structures with a funny name, the extreme learning machines. And actually, he proved a theorem saying that if one takes also a single hidden layer and you fix the internal weights to random values, then the hidden layer output matrix, whose elements are determined by the action of the transfer functions on the input space, taking in account the random distribution of the internal weights, has a full rank. And we can approximate any function with a probability 1 when the number of hidden neurons go to infinity. Okay, so this is kind of a probabilistic universal approximation theory for this kind of networks. And all in all, actually, all these schemes, the reservoir computing, extreme learning machines, RVFLNs, actually the common base of all of them is the celebrated Johnson and Lindenstrauss theorem, which actually says that if we have a set X of endpoints in Rd, then for every epsilon that belongs to 0, between 0 and 1, and K, such that K exits a certain dimension, then exists a map F such that actually the projection of X into a random subspace of dimension K preserve the distances, the difference of distances between points. So actually this difference is bounded in the interval between -1 minus epsilon and 1 plus epsilon. And actually, I note here that this mapping is a feature mapping, which is in principle may result in a dimensionality reduction if K is less than D, or a projection into a higher dimensional space if K is bigger than D, in which resembles actually kernel-based manifold learning algorithms. And actually, while the statement is interesting enough to note that while the statement of this theorem is deterministic, its proof relies on probabilistic techniques combined with Kirch-Brown's theorem to yield the so-called extension mapping. And in the original paper of Johnson and Lindenstrauss, actually they have used a linear projection. This is R, which has a dimension, is a matrix with a dimension K times D, with components which are IID random variables that they were sampled from a normal distribution. And actually, this is just one of the possible embeddings or the choice of random projection. And it has been proven also experimentally and theoretically that appropriately constructed nonlinear random embeddings may outperform simple linear random projections. Okay, so the take-home message is the heart of all these random projection neural networks is the Johnson and Lindenstrauss lemma. Okay, and now I'm going to present you after this introduction the method. So I'm going to start with a system of ordinary differential equations, and here we choose to construct a trial function psi, one for each one of the m variables of the system. See that in this problem, actually the trial function satisfies explicitly the initial values of the problem. And in our construction, the NIs are single output feed-forward neural networks with parameters, the output weights WI naught and PI containing the remaining parameters associated with that network. And actually, we seek a numerical solution based on n collocation points in the interval where we want to seek for the solution. So, as in pins, we form an objective function of this form, and actually, the different thing here is that as we fix the internal weights, the only unknowns that we get are the ones, the parameters that they are related to the weights of the linear output layer. So all the other parameters that they appear in the kernel, here, for example, we have chosen to use a radial basis function network, but also we can use also sigmoidal transfer function. So all the parameters here are fixed or in deterministically or randomly. For example, the hidden weights here are fixed to 1, and the other parameters as the centers of the Gaussian kernels are actually put as equidistant in the domain, with the number being equal to the number of the hidden nodes. The biases and the width parameters, the sigma, are actually chosen randomly from appropriately chosen uniform distributions. Actually, this kind of scheme is kind of a little bit different from the classical extreme learning machines configuration, where in the RBF structure, the internal weights are 1, but the biases are set equal to 0, and the centers actually are randomly uniform distributed in -1 and 1. Then I'm not going to show you details, but one can actually prove that for the particular structure, the particular structure is in a probabilistic way a universal approximator if one takes many hidden nodes. Actually, theoretically, this is true if the hidden nodes goes to infinity. Okay, what is the relevant advantage of this scheme and of the pins? That one can actually compute using, or here symbolic differentiation or automatic differentiation, the quantities that we need to minimize, to put in the objective function, that is the partial derivatives with respect to the collocation points, or the partial derivatives with respect to the unknown parameters. And here the unknown parameters are just the parameters of the linear output layer. So at the end of the day, what here one constructs is a random projection which here is represented by the matrix R, with elements, actually the randomized transfer functions of the hidden layer. So the output weights are projected using this random the matrix that is shaped, of course, by the input space and the fixed internal weights and biases. All right. So by doing that, one ends up with n times m nonlinear residuals. If one uses n collocations points in m variables. And of course, we can at this stage form the Jacobian, and we can solve this iteratively using a Newton-Gauss, let's say, algorithm. Here we can resort to numerical analysis tools because from the construction, usually the number of hidden nodes is bigger than the number of collocation points. So this system results to be underdetermined and not full row rank, okay? But numerical analysis tools like SVD can give us the pseudo-inverse, and then there is no problem of approximating iteratively and converge to the using the Newton-Gauss scheme, okay? And the list here is a simple adaptive scheme that we have used in order to deal with solutions that contain steep gradients when one seeks a solution in big intervals. So the adaptation scheme is very simple. Actually, what one does is that we fix the number of collocation points and try, let's say, to solve the differential equation using the proposed method in the whole interval. If the Gauss-Newton scheme will not converge in 4 or 5 iterations, then we have the interval where the solution is showed, and we repeat the Gauss-Newton iterations and so on and so forth. And when we converge, we double again the time interval and so on and so forth, all right? So I will show you the results of the scheme in different benchmark problems. I will show you 3 benchmark stiff ODEs, the Champaign-Gear problem, the van der Pol equations, and the Hires problem, which is a system of 8 nonlinear stiff ODEs, describing the morphogenesis in plant physiology. And I will also show you how our system, our method compares with established numerical solvers, both in numerical accuracy terms and computation times. Actually, I'm going to use the MATLAB ODE suite, ODE45, which is an adaptive step Runge-Kutta method based on a Dormhan-Prince pair, and the ODE15S, which implements a variable step, variable order multi-step methods, and actually is a standard way to solve steep problems, at least low-dimensional ones, okay? So the first problem is the one that was addressed in the paper of Champaign and Gear. It's a very simple one. The analytical solution, we know in this problem what it is the y equals of phi. And it can be proven that this problem is stiff if the lambda it's much less than 0. Okay. Here for our illustration, we have chosen a very simple solution, let's say, with this sine of t, and we try to solve it in 0 to pi. Okay. Again, for the implementation of the scheme, we use a trial solution which satisfies explicitly the initial conditions. And here is what we get with a random projection neural network. You see with the blue, and then this is the OD15S, and with the dust is the OD45, and then we have also the analytical solution. As we see, actually, the OD45 is close enough to the analytical solution, but with a little bit of offset. And if you see more carefully here, also the ODE15S is a little bit not exactly on the line that defines the analytical solution, while the random projection neural network visually at least is exactly on the curve that defines analytically the solution. And here is on the left, when setting both tolerances, that is the absolute and relative tolerance of convergence for all methods to 10⁻3. And on the right is when we set this tolerance to 10⁻6. Now, in more detail, in these tables, you can see first the achieved numerical accuracy of the schemes of the random projection neural network. And you see the L2, the L infinity, and the mean absolute error. And you see that in both tolerances, the proposed method actually outperforms in terms of numerical accuracy both the other methods. Of course, it would be expected to do for the classical not stiff solver, but it is interesting to note that also it outperforms the ODE15S that is actually suited for such kind of problems. And interestingly enough, here are the computational times in seconds. Think that our code is a homemade. We're not professionals. Gianluca that made that is not professional, is applied mathematician. But actually, the proposed method kind of outperformed also in terms of executional times these methods, or at least the computational times were comparable with the ODE15S. And interestingly enough, we used less collocation points than all the other two methods. See the huge number of collocation points that were needed for ODE for 45 to converge, okay? And the double points that needed ODE15S respect to our method, okay? So this is actually the first time that such results appear, and there is more. Here is about the Van der Pol equations, a classical benchmark problem for solving for testing stiff ODE solvers. Here, one can show that the stiffness is controlled by mu, and the period of the relaxation actually is of the order of mu, and this is kind of easy to show. And here are the numerical results, and here we got some very interesting things. See that here we have the combination of both stiffness, and actually stiffness is more in this range where not steep gradients arise, and then we have the appearance also of steep gradients. And in this case, actually see that the ODE15S actually fails to approximate both when we're using tolerance of 10⁻3, so 10⁻3 is A and B for Y1 and Y2, and C and D are the solutions when the relative and absolute tolerances for all schemes were set to 10⁻6. And it is interesting to see that you see here that the ODE45 seems to be on the reference solution. So the reference solution is the solution that we get with the ODE15S with the tolerance of 10 to the -14. But as we see, it needs huge computational times when the stiffness increases. So this is for mu equals to 100, the first two, and then this is for mu equals to 1000, right? But keep that in mind, that the ODE15S that was supposed to work for this kind of problems actually fails to approximate the correct pattern, okay? Actually fails to approximate the steep gradient that occurs in particular time instances, okay? And actually here are the numerical results when the tolerance were set to 10⁻3 and when tolerance were set to 10⁻6, okay, for various values of the stiffness parameter. So as you see, interestingly enough, the proposed random projection neural network outperforms both schemes for actually all the range of mu, for all the range of stiffness. And as you see, even for 10⁻⁶, we get an L2, which is really small, while the ODE 15s actually fails, resulting to big numbers. And think that this number is really small, which is the L2 norm, if you think that we have used for the particular value of the stiffness parameter more than, if Gianluca is here, more than 30 million points, okay, in order to compute these numerical accuracies, all right? And even more interestingly here actually is the computational times in seconds. So we have run 10 times this, and we have taken the median, the minimum, and the maximum times, and over 30 times mu equidistant grid points after the solution was obtained. So what I didn't tell you is that pins actually are provide analytically solution after they converge, in contrast to numerical, the traditional numerical schemes where provide just the solution only on the collocation points. And then if you want to compute a solution at a different point in the grid, then you have to do interpolation, for example. But computing the solution in different points of the grid other than the points that the pin was trained to using the collocation points is straightforward. Okay, so in that manner, pins are also faster than the other two methods, and actually their times are comparable, giving actually the same accuracy with the reference solution that was computed with the 10⁻⁴ accuracy. Okay, and then the last benchmark problem is the highest problem. This is a set of 8 nonlinear stiff ODEs, and we have the same story here. As you see here, also the adaptive Runge-Kutta becomes unstable, starts to oscillate, and the ODE 15s actually fails to approximate, at least numerically, the reference solution that again here was computed using ODE 15s with a tolerance of 10 to the -14. And here again are the results with the numerical accuracy. As you see clearly, the proposed pin random projection neural network outperforms all the other two schemes in all metrics, in the L2, in L infinity, and the mean average error. Okay, and it seems it is more robust also when we increase the required tolerance for convergence. And here actually for this comparison, we have used 150,000 equidistant grid points in the time interval of reference. And here again are the computational times. And as you see, the random projection neural network, which is actually Gianluca has done homemade, beats, let's say, the ODE, the MATLAB suite of ODE, and importantly also ODE 15s, right? Resulting to smaller computational times also when compared to the reference solution, okay? So that was, we're very happy to when we saw something like that. And then I'm going to present you some very interesting results concerning numerical accuracy and computational times when we applied this framework to solve nonlinear PDEs, okay? And actually this is, I'm not going to present you again the framework. It's similar to the one that I have presented you with for nonlinear ODEs. And the new here that is that one can actually wrap around the pins, the random projection neural network, the arsenal of the algorithms of numerical bifurcation theory in order also to construct the corresponding bifurcation diagrams. Okay, and how much time do I still have?
Like
30
15 minutes. 15 minutes.
All right. Okay. Thanks. Okay.
Because we started at 10.
All right. All right.
Yeah.
Thanks. Great. Great. Okay. So the first problem is the nonlinear viscous Berger equation. And here we have considered two different boundary conditions, the Dirichlet, gamma at the left and 0 at the right, as well as mixed boundary conditions, Neumann condition at the left boundary, where theta is also a bifurcation parameter, and 0 Dirichlet at the right. And here one can show some very nice characteristics. One of them that we can also have a unique solution in the Dirichlet case, so we can actually compare directly the performance of the numerical schemes with the analytical solution. And also for the mixed case, one can prove also analytically that at the right of the interval, one gets some very steep gradients. Actually, when theta goes to 0, the gradient goes to minus infinity on the right of the boundary. And here are some numerical solutions. Here we have used the A and B is for viscosity 0.1, while C and D is for viscosity, a very small number of viscosity, with 0.0007. And for this, for this value of viscosity, we get some very steep gradient, and where the finite differences you see here with the slide fail to approximate, actually they oscillate. And what you see here on the right column are the numerical accuracies of the various schemes. And as you see, as we increase the number of collocation points, actually the proposed scheme here, we have used the pins with both sigmoidal functions and radial basis functions. Both transfer functions result when n goes higher to much better accuracies, even better than the finite elements, okay, for this kind of problem. So you can see here the details also of the execution times. So here we have run the same thing 100 times, and we got the mean and the 5 and the 95 percentiles. And here on the left, you see the number of points that we have used for our scheme, for finite difference and for finite elements. And as you see, the execution times of the proposed scheme are shorter than the ones required with FEMS. The faster is FD, but FD fails actually to approximate the correct solution. So a comparison with FEM, which is the way to solve this kind of problems here, is that the proposed scheme is better both in execution times and in numerical accuracy as the number of points increase. And this is was something that we're very happy, and maybe this is actually also the first study that one, or maybe one of the first, that shows some such encouraging results. And then we were able to reconstruct the bifurcation diagram using the pin, the proposed pin. And guess what? We actually came with better, here the position of the bifurcation point is analytically known, so we can actually compare with the exact solution. And as the number of training points, of collocation points increase, the proposed pin random projection neural network results to the better accuracy in the approximation of the bifurcation parameter, okay? And then I will show you last the problem of Liouville-Bratoux-Gelfand problem, both in 1D and 2D dimension. This is actually an elliptic nonlinear partial differential equation. And again, for the 1D problem, one can also show that an analytical solution exists. The only thing is that one has to solve a nonlinear let's say equation with using Newton-Raphson, but this is not a problem, and also can calculate the corresponding bifurcation value where the bifurcation appears. Okay, and again, this is the resulting bifurcation parameter, and again, the proposed random projection neural network results to the better accuracy in terms of the location of the bifurcation point. And also outperforms, here we don't have a steep gradients, but it seems that the proposed scheme outperforms both finite elements and finite differences, especially when we increase the number of the mesh, okay, or when the mesh gets denser. But also, interestingly, the proposed scheme outperforms also FEMS, not only in terms of numerical accuracy, but also in terms of computational times, or at least it gives comparable execution times. Again, the finite difference is the faster, but gives the worse accuracy in terms of numerics. Okay, so this is, you can see also for the 2D problem, clearly when the mesh gets denser, the proposed random projection neural network gets better and outperforms the other two schemes. Here is the finite difference scheme, here is the finite elements, here is the scheme when using sigmoidal functions, and here the scheme when using radial basis functions. Okay, and this is also the corresponding bifurcation diagram for the 2D system. Here there is not an analytical solution in closed form, but our benchmark is values that they have been reported in many key works, for example, of Chan and Keller, regarding the value of the bifurcation point. And again, our scheme was the one that best approximating the particular location of the bifurcation point. So in concluding, we have proposed a new numerical scheme based on random projection neural networks and pins for the numerical solution of stiff ODEs and nonlinear PDs. So here at this point, I have to say that an issue here is the selection of the interval where the biases, the parameters of the radial basis functions or the sigmoidal functions have to be set. So, but when this actually range of parameters has been specified, this is kind of universal of all problems. So we use the same kind of configuration for all of these problems, and seems that it works much better than the traditional numerical methods. So actually, the scheme was takes advantage the benefits of random projection networks as universal function approximators, bypassing, here's the importance, for the expensive training of the other schemes. And we have compared this with benchmark problems and benchmark numerical analysis solvers for both of these and PDs. And we were happy to show that not only the scheme can outperform traditional schemes numerically, in terms of numerical accuracy, but also in terms of computational times. And this is also a challenging point, and a point where the machine learning algorithms have to compete with state-of-the-art traditional numerical analysis schemes. And for the time being, these are the two papers where some of the results that I have shown you have appeared, one in Journal of Scientific Computing and the other in Computer Methods in Applied and Chemical Engineering. And most of the credits of this work goes, as always, to the students that they have done most of the work, and especially Gianluca Fabiani, which is a PhD student in the School of Advanced Studies in the program of Modeling, Engineering, Risk and Complexity, and then also Angelos Galaris from the department, PhD student, Department of Mathematics and Applications. And I would also to thank my collaborators, Dr. Lucia Russo from the Consiglio Nazionale delle Ricerche, the National Research Council of Italy, and my colleague from the Department of Mathematics, Professor Francesco Calabro. So thank you for listening. I will be happy to answer to any of your questions. Thanks.
Thank you, Kostas. Any questions for our speaker?
I hope that I was in time.
Yes, perfectly. I'll start one. So I think this model will be very interesting if you can apply this to solve some ODEs equations in system biology, and maybe do you think this can be done for inferring unknown parameters in system biology, like?
Yeah, right. Thanks. So actually, this is what two things. One, actually, we are searching for solving very large-scale problems like the 3D problems that it was shown in the previous presentation. Or so, actually, it seems promising to deal with really large-scale systems, because let's say in addition to what deep learning algorithms provide in terms of, let's say, infinite numerical accuracy, this kind of seems promising also in terms of computational execution times. You can think that as you can make a relevance to what is called now, for example, randomized SVD, which is much faster than the classical SVD. Exactly. Also, the randomized SVD makes use of is based on the Johnson-Linde-Strauss theorem. So actually, this kind of fast computations that come from the random projections of your very large input space is a very interesting aspect, and we're actually trying to. So I would be happy also to, if somebody of you from your group has some big problem, so we can also deal with it. And the second, yes, we're also working on the inverse problem, right? With this kind of networks. This is also the PhD of Gianluca Fabiani. Discovering actually laws using such networks, and this is also in joint collaboration, mainly with Professor Yannis Kevrekidis from Johns Hopkins.
Thank you. Any more questions?
Yeah, this is Dr. Abdul Khalik. Thank you for a very interesting talk. I'm from Middle Tennessee State University. So the example which you gave, the stiffness, it has constant stiffness. Have you tried this on problems where stiffness is varying with the time?
Oh, this is very, very interesting and nice. Yeah. So time varying stiffness. This is interesting. No, we have not played with that, but I mean, one can. I'm trying to think the problems where you have such a thing. I mean,
chemical reactions, like that chemical reactions might change with the time. It goes fast and slow. Something
right,
like
kinetics. Yeah, right. So, for example, the work of Lam and Gusis with CSP, yeah, on chemical reactions. So, yeah, this is a really nice problem. Yeah. So the cheap answer is one can apply. I don't know the complications of applying such a scheme in let's say non-autonomous systems. But it is very interesting to think. Thanks.
Right, thank you.
So if you have some idea, I would be happy to discuss with you.
Yes, I was thinking about it, but it's too early to say something for that.
I mean, always is early before we discuss something.
Yeah, I'll be in touch with you. Thank you for a very good talk.
Thanks. Thank you. I will wait for your email. Thanks.
Any more questions?
Yeah, hi, I'm Thomas Doku. I'm
Thomas.
also working with Professor colleague at Middle Tennessee. The professor will just ask the question. You talked about computational accuracy and speed, right?
Yes.
Could you use transfer learning also to speed up?
Can you use, excuse me?
Transfer learning?
I mean, you can use more advanced, algorithms actually to speed up things, right?
Okay.
So this is one of the we have used in this step. I mean, the more standard and maybe not so appropriate for the problems, because actually also when we deal with the 2D problem, actually the scale of the system is not big one. So more advanced algorithms, for example, in the Krylov subspace or other algorithms, as you mentioned, can be used actually in a natural way with this scheme for larger scale systems like 3D. So this is now the bet, trying to solve a very large scale problems using such structures. And the bet is not only to get better numerical accuracy, because of course, if you need, I mean, one day to train the network, and then of course you can solve that. But if you can do the same thing with well-established numerical analysis methods. I mean, there is always the question why to use. But the thing is that you can use, because it seems that you can also beat the conventional way also in terms of time. And this is the bet that we should focus. Of course, an open issue here in all these things is the convergence issue, which is not trivial. So, I mean, if somebody of you, I mean, they're interested in, I will be also happy to discuss such details. Thanks.
Thank you.
I don't know if I have answered to your question.
Professor?
Yes?
I'd like to ask you related, what do you think to examine these methods related to the seismic engineering? Can you hear me?
To what? To
the seismic engineering. In the seismic engineering, we use almost the finite element method, but we don't know anything related to other methods, numerical methods. So to examine this method, what is your opinion for this?
I mean, I have an epsilon, or not epsilon, a zero knowledge on on these models in seismic engineering. So I mean, again, a cheap answer is that these methods, the pins, I mean, also the guys of the Crunch group there can also say more, that as long as you have PDs, you can try to implement and solve such system. I don't know the particularities of this kind of PDs, because some of them, they have also kind of, I don't know if this is the case in system engineering, singularities, which is not a trivial thing to do and to handle with generally, not only with pins, but also with traditional methods. So, I mean, one can try, but one, as it is physics informed, one has also to see the physics that they are modeling in the PD and take care of them.
Exactly, because I didn't see any research that deal with the seismic engineering by another method, almost another finite element method. Most of
so
them
I don't know
uses
if
the finite
Miglang, you have some or somebody of your group have some experience on this.
Not from me. Any wisdom from the group member?
But I mean, should be doable, but one should be again careful when you know when does not have the equation at hand.
Exactly. Thank you very much, Professor.
All right. Thank you, Kostas, for your wonderful talk.
Thanks. Thank you, Miglang, and thanks also George Karniadakis for inviting me. Really an honor to give a talk at the center, let's say, where the pins were born, and hope to be the start of also a collaboration.
Thank you.